Okay, here we are, geometry section 8.4. This is the last section in the chapter. For those of you taking it online, this is the last information you need to do assessment number 1 in Geometry B. So, if you're going to follow along in the book or want to reference things, this one begins on page 446, and the title of it is Proportionality Theorems. Now, you might think, if you watch the previous 3 sections, that we have all the proportionality theorems that are available. And that was the ones that we talked in the first 3 sections, the ones we talked about were only for similar triangles. There are other things in triangles, if they're formed the right way, which we're going to discuss. There are other things that we can do to triangles and create things that are still fit in a proportion. That is, A is to B as C is to D or whatever. And so we're not really going to be talking about similar triangles. And kind of we are. So you got to pay attention here and figure out when we reference similar triangles and when we don't. And the reason why I have these two drawn right next to each other is so that you can see how they are similar, but most importantly, how they are different. Now, I labeled these things parts. If you look up here, if I talk about, it depends on the context of your thinking. If you have this big old triangle here, this big monster here, and that's all you're thinking about is that triangle, and inside that triangle, you draw this line parallel to this side here. Then you have split these two sides, this big long side here and this big long side here. You have split them up when you hit it with this parallel line into 2 segments on this side and 2 segments on this side. And so I call those things parts because, yes, A is the side of a triangle, this triangle, but B is not the side of any triangle, and neither is D. They are not the sides of any triangle. So since B and D were made segments by drawing this parallel line, I'm going to think in my mind, this is one big triangle that has been split with this parallel line. And what it did is the sides that it hit split up into A and B and C and D. And what's happened here is if you have this parallel to this, then you can know for sure that A is to B. That part, that long part is to this short part, as this long part is to this short part. They are to proportion. Because parallels, this would be your reasoning if you had to justify it. Because parallel lines imply proportional parts. By drawing that line, we split it up into 4 parts. However, E and F never got split. E and F never got hit. So, well, actually, I'm jumping the gun there just a little bit. I want to show you another proportion that you could have when you make it up of strictly of side. So now you got to get another mindset, a different mindset. That is, it's not one big triangle whose sides were split by this parallel line. Now I want you to think, okay, I've got a little triangle and a bigger triangle, and they are similar to one another. I can guarantee that because they both share this side. Furthermore, this angle equals this one because of the parallel lines, and this angle equals this one. So I know that this little one is similar to the big one because of angle, which we discussed in section 8.2. So I know that this triangle is equal to are similar to the big one, which means that this short side here is to this long side, but that long side doesn't have a name. I'm going to have to call it something different, A plus B. The short side A is to its longer corresponding side A plus B, as C, this side here, is to this entire side here, which is C plus D, as this short side E is to this short side, or longer side, F. So this is sides. 3 different things are true if you compare sides. Only 2 things are true if you go with parts, because E and F are not parts. That's what I was trying to get at when I jumped the gun a little bit. So here's the deal. This is what I'm trying to get you to not do. You cannot say that A is to B. Those are parts. You cannot say that's in proportion with E and F. That is not true because E and F are sides. A and B are parts. So you can't compare parts to sides. You've either got to compare parts to parts, sides to sides, but not parts to sides. That does not work. So what I'm saying is if the 2 parallel pieces are in your proportion, if they are in there and you're trying to figure something out and it involves whether these things are known or whether it's X in here, whatever. If these parallel guys right here are involved in your proportion, you have to compare sides. That is A to A plus B as E is to F. You can't compare A and B and E and F. That's what I'm trying to get at. So that's what I'm saying right over here. So if E or F, the parallel sides, are involved in the other's ratio, proportion must also be sides. So if E and F, which can only be sides, you have to compare them to other sides. So you could compare A is to A plus B as E is to F, or you could say C is to C plus D as E is to F, because that way you're comparing sides to sides in both parts, both pieces. Okay, so let's look at example 1, try to figure out what we've got. Notice that the parallel sides are not involved at all. There's no X on them, there's no numbers on them, there's no nothing. It just seems to be the parts. So because of that, I can say question mark is to 9 as 4 is to 6. That's referring to this right up here. Parts is to parts. Okay, so this part is to this part as this part is to this part. That's legal. That's not a problem. So if I cross multiply, I get 6 question mark. That's like an X equals 36. And so question mark is 6. This length right here has to be 6. So that 6 is to 9 as 4 is to 6. Both of them in a ratio of 2 to 3. But they're parts. They're all parts because the parallel sides were not involved at all. So moving on. Example 2 is kind of weird. Look at those weird triangles. There's nothing, it's kind of difficult to see what's happening there. In example 2, it says like this. You probably want to see this in the book, but it says, on the shoe rack shown, BA is 33. CB is 27. CD is 44. And DE is 25. Explain why the shelf is not parallel to the floor. This would be the floor. Obviously, they're not parallel, but if you had to come up with a reason, it's just not poorly drawn. This would be, what we'd have to do is say, if they are parallel, then this part would compare to this one, the same as this compares to this. And so what we would put that proportion together. We would say 27 is to 33. Is that the same as 44 to 25? And again, I'm going to call on my calculator. I would say 27, and cross multiplying, 27 times 25 is 675. And I do 33 times 44. 1452. Not equal. Therefore, these are not equal. That implies that BD is not parallel to AD. Oops. BD is not parallel to AE because they're parts that are cut off by this line right here. Those parts are not even close to proportional. So, well, they have to be exactly proportional to be parallel. Here's example 3, and this one's kind of weird because it doesn't seem to involve any triangles. Well, if I connected these little tiny guys down here, they would. I'm going to erase those so that it doesn't look like they're connected. What we're talking about here is this line, and this line. We're wondering if they are parallel. This is, by the way, this is example 3, page 448, and it talks about Main Street. This is Main. This is 2nd Street. So this is 2nd Street, doesn't have anything to do with the problem. This is very strange. This one's called South Main. So it's not, that's kind of a dumb name. South Main. And then they tell us this, that this is 120 yards. This is 150 yards. I'll put yards on one of them just so we can remember the units. This is 300 yards. And here's what they want us to find out. Oh, by the way, this is a G. I left that off. And this is a D over here. And this down here is C. I left some of the stuff off when I made up the page. Sorry about that. This is E. I don't know if that's necessary, but that's all the pieces. This is everything that's offered. And here's what it says. In the diagram, angle 1, angle 2, and angle 3 are all congruent. See, I've got them all marked. This is 1, 2, and 3. And they are all congruent to each other. GF equals 120, D equals 150, and CD equals 300. Find the distance HF. Ooh, I got to find this distance here. This is HF. Right there. That's what I want to find is HF. Find the distance HF between Main Street and South Main. All right. So I already know a piece of it. It's 120. So the thing I got to find is this, and then I will add it to 120, and that'll be the answer to my question. The reason they told you that these 3 angles were equal is because they're also in a position to be corresponding to each other. If corresponding angles are equal, then the lines that form them on a single transversal are parallel. So I know now, because of the corresponding angles, I know I've got 3 parallel lines. And if I have 3 parallel lines, just like I did, let me see here. If I've got parallel lines in these triangles like I did here and here, but I got 3 of them, still splits it up into parts that are proportional. So that's kind of an extension. So this is what I would say. 120 is to X as 150 is to 3. So what I'm saying here is this is to this as this is to this, because I've got two transversals cutting these parallel lines. Now, they're not the same distance apart, obviously, but they are parallel to one another. So this part is to this one as this part is to this one. It's just an extension of what we did with triangles. Now, I can tell you right now that this is going to be 240. The reason I know that is because this is 150, and if you double that, you get 300. So over here, I would double 120 to get this, which would be 240. Or if you didn't see that, that's okay. You can cross multiply. Take 120 times 300, and that's 36,000 equals 150 times x in the cross multiplying. So I'd take the 36,000 and divide it by 150 to finish the algebra. And again, we get the 240, which we suspected because we noticed the ratio is a ratio of 2 to 1. So x is 240. That is not the answer to the question. HF is the 240 plus the 120, which is 360 yards. So make sure you answer the question, not just do the algebra. The algebra gave you a 240, but you have to come back and find out how you're going to use it to actually answer what was asked. Okay, so that's an extension of the proportionality thing. But if you've got evidence that the sides are parallel, then parts that are cut off are proportional by the two different transversals, just like they were with a triangle. Alrighty, last thing. And I've got a note to myself here, because you've got to understand this too. You have got to switch gears here. There is one other theorem that is discussed in this section, and it's unique. It's all by itself. It doesn't have anything to do with these up here, any of these proportional parts cut off by parallel lines and anything like that. It doesn't have anything to do with similar triangles, because I want you to notice in the situation I have here, this triangle is nowhere near the same shape as this triangle. There's not a parallel line to be seen. So nothing that we've discussed so far about similar triangles or parallel lines will apply here. So you have got to set this in a different file. What is true about this particular theorem is that we have an angle bisector. We have a triangle, and one of the angles has been cut exactly in half by a segment, BD. Notice that when BD hit AC, it did not cut it in half, because this is not an isosceles triangle. It didn't cut it in half, but it did cut that angle in half. So here's the deal. If you've got an angle in a triangle that's been cut exactly in half by a segment, then the two segments on the bottom that are formed when that thing hits are proportional to the two sides that they are attached to. So in other words, P is to R. This short side is to this short part, as this long side is to this longer part. You can also say this short side is to this long side. That's whole sides, as this short part is to this short part. And I know you might be thinking, she said you couldn't compare sides to parts. That's true if you're talking similar triangles, but there is no similar triangle here. We do have some parts formed by this. These are parts. These are pieces of a side that are formed when we drop that angle bisector. And they are proportional to the other two sides, short to short, long to long, short to short, long to long. And so this is a total different ball game, and you can compare sides to parts because we're not talking similar triangles here. We're talking about an angle bisector that forms these two pieces down here. Okay, so this is how we write it if we're going to write a justification for it. Angle bisectors, that's got to be present. Angle bisectors make or imply proportional sides and parts. These sides are proportional to these parts. So it's totally different than what we've been talking about, because everything else has been dependent upon parallel lines or similar triangles like we did up here, and neither one of these show up here. So this is an angle bisector theorem. It's totally different from everything else. So this is how we would do example 4, having to do with that theorem we just discussed. Notice I have an angle bisector. Also notice there's not a single parallel line, and there are no similar triangles in this, just an angle bisector. And what that means to me is one of two things. I can either say 13 is to 7, that is, long side is to long side, long side is to short side, as long part is to, oh crap, I don't have a short part. Oh, here's where your algebraic thinking comes in. If this is x and the whole dang thing is 15, then this is 15 minus x, and that you have to come up with on your own. So writing it again, I got long side is to short side, as long part x is to short part 15 minus x. You got to write it like that. If you write that, they got some proportional things going on there, then you can cross multiply. So I have 13 times 15. I'm distributing here. This times this would be 195 minus 13x. I don't know if you can see that very well on my calculator. This is what I'm taking this times this and distributing, equals this times this, which is 7x. Now I'm going to use my algebra to solve. I'm going to add the 13x over to here, and that gives me 20x. 7 and 13 is 20, equals 195. Then I'm going to take 195 divided by 20 to finish the algebra. So I get 9.75 equals x. That's this side right here. Let's see what they were trying to ask. I found a bunch of information, but I don't know what they're trying to ask. It says in the diagram, it tells us the angles are equal. These two angles right here, here and here. It tells us those two angles are equal. And it says, use the given side lengths to find the length of RS. Oh, good. RS is what we called X. I didn't write anything on here. Sorry about that. Didn't finish my diagrams. This is RS. So we were looking for this, which is exactly what we called X, which means we are done. Okay. So if I had called this X and 15 minus X, then whatever we got for X, we would have had to subtract from 15 to get this. But since I called RS X, and that's what they were asking us to find, then we've got it directly. But make sure that you go back and read what it is you're trying to find, and make sure that by finding X, you have found what you need to, or perhaps you need to substitute it in someplace. Anyway, that is the end of that lecture. And I don't have an assignment written, so I'm going to write it down right here. To practice these problems, you want to practice numbers 1 through 7 odd. For those of you taking it at Sugar Salem High School, actually at the actual school, you have to do this assignment. 13 to 25 odd, and 29 and 30. So there you go. Good luck. Please let me know if I can help. I'm happy to look at things with you. See you later.